Good afternoon. This is lesson 5 of the course Industrial Instrumentation, and in this lesson we will cover the load cell. Load cell is very important devices. It is basically a mass measuring or weight measuring instrument or sensor, whatever you say, using the principle of strain gauges. You have seen that in the lesson 4 we have covered strain gauge in details. So, using the strain gauges, now you will see that how we can make a load measuring devices. Now, it is a very simple form of instrument, and that are the advantages of this instrument, that it is simple, it can have a wide range, it is a linear instrument, and it has it can operate in the dusty and the corrosive environment. These are the some advantages of this particular instrument. You can see if you move in a highway that there are load cells and weigh bridges, basically you will find where they used to take the weight of the truck or how much load the truck is actually carrying, they can find in the load cell. If you know the tare weight or empty weight of the truck, so that you can find how much load it is carrying. It is also used in the measurements of the load in the wagon on line, I mean continuous measurements of the wagon, I mean how much weight they are in the wagon, all those things, and it is possible with this type of instrument. Basically, we will cover there are the two types of load cells. The first is the link type load cell, and secondly we will cover the beam type load cell. Now, link type load cell usually we will find it is used for measurements of the large load, whereas beam type load cell is used for the measurements of the small load. Now, there are other type of load cell like ring type load cells, all those things, but due to the restrictions of the, because same principle is basically same, that is the reason we have taken two different load cells and cover it in the in this particular lesson. Now, so far the disadvantages are concerned, there is only one disadvantage, which is the phenomena called the creep. Now, creep is basically that it actually is a permanent deformation of the load cell if a load is applied to a particular cell for a quite long time. That does not happen in the case of in the case of weigh bridges and all this, because the truck will move and after some time the truck will go away. So, but if by chance if you apply a load permanently, there is a chance of deformations, which will lead to the drift of the instrument, zero drift of the instruments and all this. So, you have to be very careful about that. The careful selection of the also the material of the load cell also can prevent that type of problem. Now, there are two basic type of loads. So, one is so far the ranges are concerned, one is for the small load, suppose from 500 gram to you can measure up to 5 kg, and others you can measure suppose 10 kg to even 1000 tons. That type of load cells are also possible. Now, contents are, we will first cover the unbalanced Wheatstone bridge, because we will use here the unbalanced Wheatstone bridge, that is the reason we have discussed the unbalanced Wheatstone bridge here. Then we will cover the column type load cell, instead of link type load cell I mentioned it is a column type load. Sometimes some people call it the uniaxial link type load cell, some people call column type load cells. It looks like a column, that is the reason it is more appropriate if I call it as a column type load cell. Then we will cover the cantilever beam type load cell, because it is basically a cantilever on which the sensor are used, that is the reason it is called cantilever beam type load cell. At the end of this lesson, the viewer will know installation of strain gauges on load cell, how the load cells will be installed on this is very important to make the sensitivity high, also to get proper output. You will see that if the orientation is something different, whatever we have prescribed here in the case of column type load cell, you will find there is no output. So, orientation is very important for making a load cell, because strain gauges are basic sense are there, and it will make the complete instrument of load cell. Sensitivity of the load cell, every time, I mean in the both the cases, in the case of column type load cell as well as in the beam, I mean in the cantilever beam type load cells, we will compute the sensitivity of the load cell. Okay. Sensitivity means the load cell as well as the Wheatstone bridge combination, because ultimately we will measure this unbalanced voltage by means of Wheatstone bridge, and that unbalanced voltage will be calibrated in terms of load. Range of the load cell, all that you will find that there are different load, I mean different range of the load cell, that also, and fatigue strength, all these things is very important to find the range of the load cell. And you will see that in the case of column type load cells, the range is much more than the beam type load cell. Now, as I told you that you will use basically Wheatstone bridge in the load cell. The Wheatstone bridge is commonly used to convert a change in resistance to an output voltage, that we have seen in the case of simple balanced Wheatstone bridge. So, here we will use the unbalanced Wheatstone bridge. You see, this is our basic Wheatstone bridge circuits, and you can see here that we have used 4 resistance. This is R1, one resistance, then we have R2, then we have R3 and R4, and we have used an excitation EEX. So, we have written EEX, that is excitation voltage. We can use DC voltage as well as AC voltage, that does not matter, because ultimately you will get a resistance. It is, if it is, so far it is a pure resistance, it hardly matters whether you are using a DC or AC voltages. Here we have used a DC voltage, and this is the unbalanced voltage of the bridge. So, this voltage E naught will be calibrated in terms of the load, which actually we are going to measure by this instrument. Now, with an initially balanced bridge, we can say that output voltage E naught develops when the resistance R1, R2, R3 and R4 are varied by the amount delta R1, delta R2, delta R3 and delta R4 respectively. You will get, with the new values of the resistances, change in output voltage can be expressed as E naught equal to R1 plus delta R1 R3 plus delta R3 minus R2 plus delta R2 multiplied by R4 in plus delta R4 upon R1 plus delta R1 R2 plus delta R2 whole in the parenthesis multiplied by R3 delta plus delta R3 plus delta R4 plus delta R4 whole multiplied by the excitation voltage E subscript X. Substituting for initially balanced bridge, we can assume that if the bridge is initially balanced, usually in the standard load cells we will find that we will take all the 4 resistance equal. It is not necessarily you have to you have to make it equal, because as you know the basic principle Wheatstone bridge, the bridge will be more sensitive when it is all the resistance were almost equal. Otherwise, you can say that when R1 into R3 equal to R2 into R4, this is also the initial balance condition of the bridge. Now, E naught output voltage or unbalanced voltage can be given by small r divided by 1 plus r whole square whole multiplied by delta R1 plus R1 minus delta R2 by R2 plus delta R3 by R3 and delta R4 by R4 into Ex is subscript Ex. This is equation number 1. This equation is very important, because you see that by looking at this negative term, we can tell that actually where I will put this raised R2 and R4, because that will make our bridge output much higher, because we always want in any instrumentation system that the output should be higher and higher, so that our sensitivity will be high and high. And where small r equal to R2 by R1. So, if all the resistance are initially equal, that means R1 equal to R2 equal to R3 equal to R4. So, in that type of situation, this will be simply 1, right. Now, you may say that if I use I mean we have used 3 bridges, I mean 4 bridges, 4 resistance, I can use 1 resistance also in the case of Wheatstone bridge. However, suppose I have a I mean I can simply use a, so instead of using 4 gauges, I can use only 1 gauges also. Suppose this is R1, this is R2, this is R3, this is R4. So, if these are the, if R1 is the basic, I mean our strain gauges, suppose R2, R3, R4 are the fixed resistance. In that situation, you will find that all these terms, that means delta R2 by R2, delta R3 by R3, delta R4 by R4 all will be 0, right. So, our output will be E naught equal to delta R1 by R1 multiplied by 1 by 4 into E Ex, E subscript Ex. So, you can see that if I use 4 bridges, so I can make the sensitivity almost 4 times. You will find that this is very much true. Now, let us derive this equation, that means the equation number 1, how we got it actually, this equation, that is very important equations of unbalanced Wheatstone bridge. So, let us derive that. Suppose these equations I am writing, I am first drawing the Wheatstone bridge. This is R1, so it looks like, so this is our output voltage E naught. I can use a simple multimeter to measure that voltage, and I gave the this name Ex, and this terminal is node is A, this node is B, this node is C, and this node is D. So, if you have this type of equations, quite obviously I can write that E A V, that is voltage between this resistance R1, is equal to R1 by R1 plus R2 into multiplied by Ex. So, it does not matter whether it is balanced or unbalanced, it's so always this is true. Similarly, the potential across the resistance R4, which can be derived as EAD equal to, this is separate, EAD equal to R4 upon R3 plus R4, that means current flowing to this path multiplied by it is the E subscript Ex. Now, the output voltage, I can take a new page, the output voltage, therefore, the output voltage V D equal to E A B minus E A D, which I can write simply R1 minus upon R1 plus R2 minus R4 upon R3 plus R4 Ex equal to R1 into R3 minus R2 into R4 upon R1 plus R2 R3 plus R4 multiplied with the excitation voltage Ex, right. So, these two terms, I mean you see that R1 R4 and R4 R1 are cancelled out, So, if initially the bridge is balanced, if I say that the R 1 R 3 R 2 equal to R 4, as I told you earlier, not necessarily all the resistance will be, necessarily it will be equal. If this condition is fulfilled, that all, then also the bridge is balanced. So, the output E naught will be 0, right. Now, suppose all the resistance are getting varied, as it happens in the case of load cell, both in the case of column type load cell and the link type load cell, all the 4 resistance are getting varied. If it is, so we assume that the resistance R 1, R 2, R 3 and R 4 are varied by delta R 1, delta R 2, delta R 3 and delta R 4 respectively. So, my output voltage will look like, you see, E naught will be equal to R 1 plus delta R 1 multiplied by R 3 plus delta R 3 minus R 2 plus delta R 2 R 4 plus delta R 4 upon R 1 plus delta R 1, sorry, this is I do not know. Okay. Oh, I am sorry again. So, there should be actually a plus sign. Yes, plus R 2 plus delta R 2 R 3 plus delta R 3 R 4 plus delta R 4. So, if I take R 1 into R 3 common in the from the numerator, R 1 R 3 1 plus delta R 1 by R 1 1 plus R 3 minus R 2 R 4 1 plus R 2 by R 2 1 plus delta R 4 by R 4 bracket closed upon all same R 1 plus delta R 1 plus R 2 plus delta R 2 R 3 plus delta R 3 R 4 plus delta R 4, right. So, this almost we can write because delta R 1 and delta R 3 will be very small. So, the multiplication of these two terms we neglect. So, this equation almost will be equal to R 1 R 3 1 plus delta R 1 by R 1 plus delta R 3 by R 3 minus R 2 R 4 1 plus delta R 2 by R 2 plus delta R 4 by R 4, right. Here also we neglect the term multiplication term, that means R 2 product of delta R 2 and delta R 4, since this will be quite small, upon same denominator R 1 plus delta R1 R2 plus delta R2 R3 plus delta R3 plus R4 plus delta R4, clear. So, R1 R3 1 plus, okay, yes, take a new page again. So, since the bridge is balanced, we can write R1 initially the bridge is balanced, R2 R4 initially, when bridge is balanced, I can write the expression output E naught will be equal to R1 R3 delta R1 by R1 minus delta R2 by R2 delta R3 by R3 minus delta R4 by R4 upon R1 plus R2 multiplied by R3 plus R4. So, if I take from the delta R1 by R1 minus delta R2 by R2 plus delta R3 by R3 delta R4 by R4, if I take R1 R3 common from the denominator, 1 plus R2 by R1 multiplied by 1 plus R4 by R3, like this one. We assume that the ratio, if we assume ratio R2 by R1 equal to small r, then output voltage will be equal to delta R1 by R1 delta R2 by R2 plus delta R3 by R3 minus delta R4 by R4 upon 1 plus R 1 plus 1 by R Ex. So, this will give us the equation R 1 plus R whole square delta R 1 by R 1 minus delta R 2. I can erase this part again. So, it will be delta R2 by R2 plus delta R3 by R3 minus delta R4 by R4 into Ex. These expressions we have the first we have shown in a basic. These equations will be utilized for all unbalanced Wheatstone bridge, right. So, in both the case of the column type load cell as well as in the beam type load cell, we will use this unbalanced Wheatstone bridge equation. And it depends, as you know, that if you make only 2 gauges, in that case delta R3 and delta R4 by R4 can be cancelled out. I mean, you can use a fixed resistance. In that case, our output will be obviously less, but if you use 4 gauges, you will get temperature compensation as well as the output will be more. as you know, for in the Wheatstone bridge, to make that, because strain gauge is basically very temperature sensitive, since it is a resistance changes with temperature. But we want that the resistance will change only when we will apply the load to that load cell. So, the temperature effect should be nullified. For that reasons, we have used that ambient temperature compensation scheme. So, for ambient temperature compensation, at least I need 2 gauges. One gauge can be active, other gauge can be passive also. That means, it can be dummy, even though it is made of strain gauges, but that may not be subjected to load. In that case, I will get temperature compensation, whereas in the case if I use 2 active gauges, then you will get temperature compensation, as well as my output will be doubled. But if you use 4 gauges, I will get temperature compensation, as my output also will be 4 times. In the case of you will see that in the case of in the case of beam type load cell only, that I will get the output almost 4 times. Now, let us go back to our. So, this was our final expressions we have seen, right. So, I can choose some other pen. Yes. Now, column type load cell, a simple uniaxial column type load cell is shown in figure 5.2. Load can be either tensile or compressive, because it depends on the where you will apply the load. If you apply the load on the top of the load cell, it obviously the bottom of the load cell should be fixed. So, in that case it is a compressive load, whereas if you suspend the load from the bottom of the our load cell, that means our column type load cell, it will be a load of elongation. So, in that case it is not more a compressive load, it is a load of elongation. So, that is the reason we are call it either tensile. It does not matter, our expression, either final expressions of the Wheatstone bridge will remain same. The strain gauges 1 and 3 will show are subjected to axial strain, and gauges 2 and 4 subjected to the transverse strain. You see that this is a column type load cell, which is figure 2. Now, you see here that, let me take a pen. Yes. You see here this strain gauge, here this strain gauge, it is shown like this one, whereas this is shown like. So, these strain gauges, and there is similarly there is another, because if you take, there are 4 faces of a load cell, and this load cell, it appears that it is subjected to the tensile load, okay, or elongations. Now, what will happen, you see that in this case this load cell will be subjected to axial strain. Now, there are similarly you will find the other side, because there are 4 pages and you cannot see the faces 3 and 4 of this strain of this load cell. So, in the faces 3 also, that is the back side of this one, also there is another strain gauges which is subjected to axial strain, whereas gauge number 4 will be subjected to the transverse strain, right. And this is axial, that is the reason we call it axial strain. This is resistance R1, R2, R3 and R4. This is subjected to axial strain, this is subject to transverse strain. Gauge number 3 again is subjected to axial strain, and gauge number 4 will subjected to transverse strain. Now, orientation of the gauges, this is like this will be like this. So, other side, that means on the face 3, so it will be axial. So, it will again up, that means it will look like this, whereas in the case of gauge it is a 3, in the case of gauge 4. So, it will look like this, right. So, this will be subject to transverse strain, and whereas this will be subjected to tensile strain, because these are all, since as shown in the figure. So, it is subjected to tension. So, it will be tensile strain, right, and now we have put in a Wheatstone which looks like this one. Now, see what is very interesting factor, that if I put all the strain gauges in the axial direction, then what will happen? If I put all the strain gauges, that means this gauge number 2, gauge number 1, gauge number 2, gauge number 3, suppose all are subjected to axial strain, then what will happen? Interestingly, we will find the output will be identically 0, is not it? You can apply in our Wheatstone bridge, unbalanced Wheatstone bridge equations, equation number 1 probably. So, we will find that the output will be 0, that we do not want. That is the reason we have changed the orientation of the gauges, whereas in the case of beam type cantilever beam type load cell, you will find the all the gauges are in the same directions, all are subjected to axial. Obviously, 2 will be compressive and 2 will be under tensile load. If it is there, so I can say that now axial strain, you see it is given by epsilon A e A x, we write P upon A into E, right. Now, see, and we have written like this E A x, so that it can easily devise E x means axial. Now, transverse strain is given by nu P upon A e. Now, what are those legends? Let us look at, where A is the cross sectional area of the link. Okay, we have seen the link. So, the link looks like this, is not it? So, this area is the cross sectional area is A, right. E is the modulus of elasticity of the link material, right. Then we have Poisson's ratio nu of the link material, and P, as you know, is a load basically, it is a load on the. So, I can write delta R 1 by R 1 equal to delta R 3 by R 3 equal to lambda into epsilon E x equal to lambda P by A e. This is coming from the simple our strain gauge formula. Since delta R 1 and R 3 are initially same, we can assume the delta R 1 by R 1, because you see it is very carefully both R 1 and R 3 are under axial load, right. So, whatever the value of R delta R 1 by R 1, it will be similar to delta R 3 by R 3, right. So, it is multiplied by the lambda, which is lambda is the gauge factor of the strain gauge materials, multiplied by the strain will be equal to lambda P by A e, and delta R 2 by R 2 will be equal to delta R 4 by R 4 equal to lambda into epsilon transverse, that means transverse strain equal to minus nu lambda P by E. This is coming from the basic formula which we have discussed when we in the lesson 4 actually, when we discuss the load cell, when we discuss the strain gauges. Well, lambda is the gauge factor of the strain gauges used in the load cell, right. So, the output voltage E can be expressed in terms of the load P, assuming R 1 equal to R 2 in equation 1. So, if you put all these values of delta R 1 by R 1, delta R 2 by R 2, delta R 3 by R 3 and delta R 4 by R 4 in equation 1, we will get output voltage E naught equal to lambda P multiplied by 1 plus nu E subscript E x excitation voltage upon 2 A E, right. So, you see it is a basically very linear instruments. If you look at very carefully, the P is a load actually, lambda is a strain gauge, depends on the strain gauge. Usually if you use advanced, it is lambda equal to 2. The Poisson's ratio, this is also constant. Supply voltage, DC supply voltage, this is also constant. Area of cross section of the link, this is also constant. Young's modulus of the material, this basically. So, you can interestingly see nu and E will depends on the link material, where lambda will depend on the strain gauges type of. So, these are all constants. So, you will find that the output voltage E x also, if the supply voltage remains constant, if you use a battery, so obviously it will remain constant, output voltage is directly proportional to P, right. This is very important, because it will make us very simplified signal processing. So, it will be it is basically coming under a category of the linear instrument. Or I can little manipulate. So, I can write P equal to 2 A E upon lambda 1 plus nu multiplied by E x into E naught C E naught, where C is called the calibration constant of the load cell. Therefore, load P is linearly proportional to the output voltage E naught, and the calibration constant is C is equal to 2 A E lambda 1 plus nu into E x. So, obviously, you can see that the sensitivity of the load cell withstand bridge combination, there is no use of having only load cell. So, if you combine these two and tell the its sensitivity is given by S equal to E naught by P is the load 1 by C lambda 1 plus nu E x by 2 A. Very important equations if I look at. So, you see this is our equations. Now, you see that one thing is very important, that sensitivity can be increased by increasing the lambda. Poisson's ratio, it is hardly, it does not matter much because it is around very small, 0.3 in the case of steel. Supply voltage we can increase, because if you increase the supply voltage, obviously our output voltage will also increase, or we can decrease the value of A and E, right. A we can decrease, that is area of cross section of the load cell we can decrease, I mean uniax our column type load cell also we can decrease. Young's modulus of elasticity of the material. So, we can choose material in such a way the Young's modulus of elasticity is also lower. So, in that case our sensitivity will increase. But one thing is very important, you see that in the case of I cannot increase the supply voltage or excitation to my bridge indefinitely, because what will happen, you see each strain gauge has a resistance, basically it is a resistance. So, it has a current limitation, how much current I mean will pass through. So, if I increase E x, so please note that in since it is two resistance are in series, obviously what will happen that the current through the each of the gauges will increase. So, you have to look at that this current should lie within the limit, or the if I square r if you take, so that it should remain within the range of the dissipation of the strain gauges. So, I cannot increase it indefinitely, it has some prescribed. So, usually what we do is if we find that the we know the resistance of the strain gauges, and if you know the current allowable current to the strain gauges, accordingly we choose the power supply. So, that under no condition it will cross the current limit, right. Now, interestingly you cannot decrease 2 and E. You will see that if you decrease 2 and A and E, you will decrease the range of your load cell. And one important thing, you see that load cell looks like this. If it is on the compressive load, one thing you should mention, because we already discussed the tensile load. If it is under the compressive load, so it should not buckle. Usually what you will fix this point and give a force on this side. So, the load cell should not get a shape like this one, right. So, that will create problems. So, that it should not buckle. So, if you decrease that A and E, you will find there is a chance of that type of formations which will damage all our equations, or whatever the equations which are that no more valid in that type of situations. This arrangement gives a sensitivity 2 into 1 plus nu times that achieved with a single active gauge in the bridge. We have seen that if you use a single bridge, because you see here if I go to the previous slide, you will find that you can see that this one, that this 2 nu 2 into 1 plus nu times that achieved with a single active gauges, it is true, because in the case of single gauges, so you will find the sensitivity will be much lower, right. It also provides temperature compensation, as I told you earlier, since all the 4 gauges are at the same temperature. The equation to indicate sensitivity of the column type load cell depends upon cross sectional area A, modulus of elasticity, and Poisson's ratio of the column, gauge factor of the strain gauges, that means lambda, and excitation voltage of the bridges. Now, range of the link type load cell or column type load cell, both way we can see it, either we can take column type load cell or we can get link type load cell, is given by P max equal to S subscript F s into A, where SFS is called the fatigue strength of material of the load cell, right. So, if you compare this equation with the previous equation, that means sensitivity as well as the range, if I compare side by side sensitivity and range, because this will give the range, P max is the range of your load cell, you will find that if the sensitivity is high, our range will be low and vice versa, right. That means low range of the load cell, that means I mean infer that the high sensitivity is associated with the low range of the load cell, while low sensitivity is associated with the high range of the load cell. The voltage ratio at maximum load E naught upon E subscript T x maximum for the column type load cell, which combinations will be given by E naught by E x maximum lambda SFS, I mean fatigue strain 1 plus nu by 2 E. Now, load cells are usually fabricated from steel with following specifications. So, E Young's modulus is 2.0684 into 10 to the 11 newtons per meter square, nu equal to 0.3 Poisson's ratio. I mean fatigue strength equal to 5.516 into 10 to the 8 Newton per meter square, lambda equal to 2 for the advance. If the strain gauge is made of advance, so the gauge factor will be 2. So, we have taken lambda equal to 2. In that situations, you will find that E naught by E x maximum is equal to 3.47 millivolt per volt, right. So, this is our expressions. Now, some important points. Now, see under the deflections of the column type load cells under the full load is of the order of 0.025 millimeter to 0.38 millimeter, extremely small, because it has a high stiffness, and therefore, natural frequency of the load cell is not very important. It will be determined by the force carrying elements such as wave bridges, because that itself carries, I mean a lot of its mass is much more higher than the load cell itself. So, frequency, all these things will be covered, will be determined by that platform itself. Now, some important features you see that to achieve the high accuracy, additional temperature compensations will be required as shown in the following figure. Some additional circuits is a modified Wheatstone bridge for additional temperature compensation is necessary, because you will find it may happen that all the resistance may not have the same temperature coefficient of resistance. So, in that type of situation, so we have added, actually you will find very carefully only three resistance R x, R y and R z, probably all will be the varying sort of resistance. Okay. R x and R y are the temperature sensitivity resistors, and R x is the compensates slightly different temperature coefficient of resistances. R y, it is a non-temperature sensitive resistors, and it will provide desired sensitivity. I can control the sensitivity by that, and this is our cantilever beam type load cell that ends the previous ends the. Now, cantilever beam type load cell, you see that this is actually a cantilever, you can see here, this is a cantilever, and we have installed, we have applied a force P, right. So, it looks like that the you will find it previously like this, now it will bend like this, is not it. It appears, you see, if I apply the load P here, this side is bending more, that free end, this is a fixed end, but you see very carefully that the strain gauges were installed very close to the hinge point, that means strain gauges are installed here, okay, so here also in the bottom also there are two strain gauges. The reason is stress is maximum at this point, not at this point. The stress is not maximum at this point, or stress gradient is also at maximum at this point, but not at this point. So, that is the reason we install the strain gauges in these directions. Now, you see that here also we have used 4 strain gauges, 1 and 3 on the top and 2 and 4 at the bottom of the strain gauge. It cannot see from the top. So, 2 and 4 at the bottom of the strain gauges, bottom of this cantilever beam type load cell, right. So, you see that if I apply a force here at this point, okay, at the extreme end, the strain gauges 1 and 3 will be subjected to tensile load, whereas strain gauges 2 and 4 are subjected to compressive load, right. And we have taken a dimensions, that means this is width is W of the strain gauge of the this cantilever, height is H, and I am applying a force which is almost from the midpoint, if I take at a distance of x from the midpoint of the strain gauges. Okay. So, this is called the cantilever beam type load cell. Let us do the analysis. So, orientation of all strain gauges are in axial direction, this is more important. Okay. In the case of column type or link type load cell, we have seen that the gauge 1 and 3 are in axial directions, whereas gauge 2 and 4 are in the transverse directions, the orientations, whereas here all in axial direction. The gauges 2 and 4 on the bottom surface of the beam. The resistance of the gauges 1, 2, 3 and 4 are assumed that the R1, R2, R3 and R4 respectively. Moreover, in the unstrained conditions, R1 equal to R2 equal to R3 equal to R4, there is no force applied on this gauge. So, R1 equal to R2, R3 equal to R4, and gauge, interestingly, gauge 1 and 3 will be subjected to elongation, whereas gauge 1, 2 and 4 will be subjected to compression, because it is on the bottom, so it will be subjected to compression. This is our strain gauge circuits. You can see Ex, you see here. So, strain gauge R1, strain gauge 1, actually it should be on the parenthesis, and this will be like this one. Same excitation voltage we have given, and I am getting output voltage E naught, right. Now, you see that we have already seen that gauge 1 and 3 will be at the top, it will be subjected to the tensile load, whereas gauge 2 and 4 as the bottom surface of the cantilever beam, it is subjected to compressive load. If that is the situation, so I can see that I will get the load P produces a moment of P into x. So, the strain developed at the gauges are given by epsilon 1 equal to minus epsilon 2, since it is under elongation, this is under compression. So, these are same in magnitude if the initial value is same, but opposite in sign, equal to E 3 equal to minus E 4, 6 P x divided by E W h square, where W is the width of the cross section of the beam, h is the height of the cross section of the beam, and the change of resistance in the gauges will be given by, you see, change of resistance of the gauges will be given by delta R1 by R1 equal to minus delta R2 by R2 equal to delta R3 by R3 equal to minus delta R4 by R4 equal to 6 lambda P x by E W h square, which is equation number 4. Substituting equation 4 in the expression for unbalanced switch which you have derived sometime later, the output voltage can be written as simply E naught equal to 6 lambda P x, because already there is negative sign in front of the delta R2 by R2. So, it will become all will become positive, 6 lambda P x by E subscript T x equal E W h square, where is the Young's modulus. So, P equal to E W h square equal upon 6 lambda x into E x into E naught. So, the P is proportional to E naught. Again it tells that it is a linear sensor, you see here it is a linear sensor. P is proportional to E naught, so obviously it is a linear. Again let us find the sensitivity. Sensitivity of the cantilever beam type load cell and Wheatstone bridge combinations will be E naught by P equal to 6 lambda S E x E W h square. So, as it happens as before, that if we reduce E, W and H, so obviously our sensitivity will increase, but if we decrease W and H, there is little chance of reducing E, because we will use some steel. So, we can only manipulate W by H square, W and H square if I reduce WH, our range of the instrument will also reduce, right. Similarly, I cannot increase E excitation indefinitely, because this will create the problem of that it may cross the limit of the current limit of the strain gauges. Sensitivity depends on the shape of the beam. Shape means WH, that is the shape of the beam, and the point of applications of the Young's modulus of the elasticity of the material of the beam, and the gauge factor, and the point of application of the load, because it is x is the point of application of the load. So, it looks like this. You see, this is our x, this is lambda, this is WH. Okay. Sorry, this is WH, and you can take I do not know. Yes, Young's modulus of elasticity. So, it actually basically will depend on E. So, it will depend on sorry. Anyway, it is depends on the Young's modulus of the material. The range of the cantilever beam for measurement of load is P max equal to SFS WH square by 6x, and this is the range. So, obviously, it depends on the fatigue factor, the voltage ratio at the maximum. So, you can see that it depends on the so many other points like fatigue factors and all these things. So, you can see here this will depends on all this WH and 6. So, voltage ratio at the maximum load is given by So, voltage ratio at maximum load is E naught upon E x max equal to lambda SFS by E. Now, there are, even though we discussed about the all the electrical load cells, there are pneumatic and hydraulic load cells are also there, even though not much in popular. There are Indelian load cells, we call it Indelian load cell. If you have to add some factors on this one, it looks like that it can be formed by adding a microcontroller to a standard cell. So, you know, the microcontrollers is basically, there are two types of microcontroller available. In many cases in instrumentations, you will find we use microcontrollers. Now, microcontrollers is nothing but a microprocessor, but with some additional peripheral chips built in. It is some sort of embedded systems also, because those peripheral chips are there. Now, one of the popular microcontroller, as you know, is 8051, which is basically an 8-bit microprocessors along with the certain amount of RAM. It has a very small RAM, 128 byte RAM, then 2 counters. So, all those peripheral chips are inside this machine. So, you can use it for measurements of for many control mechanisms. Now, this is very important, because if you need little bit of computations, suppose in the case because we are nobody uses a microprocessor, you use a microcontroller. There are two types of microcontroller available, the 8-bit microcontrollers and 16-bit microcontrollers. 8051 or 8091 is basically almost same, but it has the features, it is basically 8-bit machines, 8-bit microcontrollers, and because there is no use of using 8-bit microprocessor. And you will find incidentally that 8-bit microcontroller can function so much that it can do so much computations. We do not need 16-bit microcontrollers. So, if it can be added, as it said, the Indelian load cells, I can make it can be formed by adding a microcontroller to a standard cell, right. It can calculate display total cost from the measured weight using stored cost per unit weight information, because ultimately those will take the reading of their truck. So, they have to must pay. So, that it depends on how much load you are carrying. So, depends on that usually they pay. So, it can be, we can all the scale factors, different things, if there is certain amount of non-negative, also can be solved with the use of microcontrollers, right. So, this is called the intelligent load. So, this is not new for the load cell. I mean, all intelligent sensors, all intelligent machines, and it has some inbuilt computational facilities. So, if you use a microcontrollers, then we will call it intelligent machines. Now, cost per weight can be stored for a large number of substances, making the instrument very flexible in its applications. This is also is not true for only for this type of load cells. You will find in many applications you can do it. That means suppose if you you can make a machines, that means all the weights are selected, all the weights are there, or you all the cost of the per unit volume per kg of the different materials are there, especially in the grocery store and all this thing. Abroad you will find these type of things are there, that you can choose the particular cost and can calculate and make the total value of your material whatever you have bought. So, this is all about the our intelligent load cells, and it is very extensively used. So, we basically discussed two basic load cells, that means the link type as well as your cantilever beam type load cell. As I told you earlier, the link type load cell, or sometimes people call link type load cell, sometimes people call it column type load cell, and other is a cantilever beam type load cell. You will usually find that the cantilever beam type load cell used for the less load, slightly lesser load, whereas the column type load cells are usually used for the larger loads, right. This ends the lesson 5 of industrial instrumentation.